Again, good afternoon. So for this last presentation for our academic lecture this term, the title of the presentation is Curriculum Learning for Image Classification. So we started with object segmentation. We've gone through 2 lectures on object detection. Now for the last discussion, this would be more on the image classification task. And the curriculum learning is actually a learning paradigm that trains machine learning models the same way that humans learn, by starting with easier problems and gradually increasing the difficulty. This strategy has shown to improve generalization and convergence rate for a variety of models in computer vision and other fields. The lecture that we're going to have right now will cover the core concepts behind curriculum learning, including the history, maybe the motivation, variations, and applications. So the presenter for this lecture would be Christian. Christian is an undergraduate student in the BSMS Computer Science program at DLSU University. His research focuses on automated diabetic retinopathy classification and how it can be optimized in low resource settings using smartphone-based fundus imaging. So I am now giving the floor to Christian. You may start your presentation.
All right, good afternoon, everyone. Like was mentioned, I'll be discussing curriculum learning, specifically for image classification as well. I think everything is good. Everything's visible. Uh, yeah, so uh, to begin, we can first look at how traditional machine learning models typically use the training set in order to train the model and adjust its weights. So we'll be focusing specifically on this section right here of training, where we're ordering or deciding what images to show to the model at each training step, and how those are ordered and decided, right? So as you may know already, every epoch of the training cycle, we pass through the entire training set, and this is done in iterations of randomly sampled batches. And so the model adjusts its weights per batch based on that batch's average loss. And we do this iteratively and in multiple cycles until we're satisfied with the model's performance, based on like some criteria, like if the model is converged or a certain like criteria has been met. So yeah, like I mentioned, we're training examples that are, well, the training examples are randomly presented to the model. And the issue with this is that it ignores two important pieces of information. First, it ignores the complexities of the data samples. So as us as the researchers, we may have some prior knowledge on how the training distribution is set. So we could know that some images are um, have like very simple backgrounds, or some images may have like multiple objects in them. And by randomly selecting per batch which images to show to the model, we kind of ignore the potential. We forfeit the ability to use this information to benefit the model during training. Second, we're also ignoring the current learning status of the model. So during training, right from the start, when all the weights have just been initialized, we're already showing all of the images, and we don't really care what we're showing the model. So everything is weighted equally since we're getting averages per batch. So let's say at some point the model becomes real good at like detecting a specific class. Maybe this class has been overrepresented. However, in a poorer performing class, an example from a poorer performing class versus an example from a good, well-performing class, they're still weighted equally. So we're once again ignoring the learning status of the model, and we're forfeiting that ability to leverage the performance of the model during training. So in comparison, let's just look at how humans are learn typically. So I have here an example of my flowchart from LaSalle, and obviously, I mean, it's immediately apparent that there's many arrows which indicate hard prerequisites, and a hard prerequisite would mean that you have to have taken like the class before the arrow before taking the next class. And the university does this because it knows that there is a benefit, or um, there must be a meaningful order at which students are presented information in order to promote better learning and better understanding. So, for example, the PROG series, which I think a lot of you have taken, at the start, you obviously start with basic concepts like data types, like syntax and C, etc. And then eventually, as you finish that course, then you move on to more specialized concepts like, I guess, object-oriented programming in Prog 3, I think. And so if we take that concept of learning via curriculum, then that's how we arrive at curriculum learning with machine learning models. And here I have a basic diagram on how curriculum learning is done with our data set. So the curriculum is divided into multiple steps. So a Q represents a training distribution at step T. So at Q1, the first step, that's when we start with a small and easy subset of the data. So as you can see here, from the entire data set, let's say there's 12 images here. We're only actually taking a third of the examples. And this third would be like the third easiest examples from the set. And you can see that from like an objective standpoint, I guess you could say that it's easier because the background is plain. There's very limited objects per image. Like, there's one fruit, and then there's only one of them that has two fruits. So it's very clear the silhouette is defined, and so the model could gain a lot from understanding like the shapes of the fruits without the noise of a background. And at some defined point, we could decide that the model is mature enough and is ready to move on to larger and harder subsets of the data. And at that point, we'd add on harder images. And here we are still including the subset from previous steps, and we're simply adding on more difficult examples until eventually we reach the point where the model is mature enough. You can see like it has learned some weights here, and it's ready for the entire training set. And that's when you're done with the curriculum. So the curriculum must always end with using the entire training set. So yeah, that's the process that I've summarized. You train on the model on small subset of easy images, and then as it progresses, you add on the harder images, and you continue until the entire data set is used up. And there's three main benefits to this, and we'll go into the why, or like why these benefits come about in later slides. But the first benefit is that it can lead to improved model performance, and second, it can lead to faster training times. So, for example, I read about it's one of the references later on, but a curriculum was used to help a neural machine translation model reduce training time by up to 70%. And so with that, it's not only limited to image classification. The benefits of curriculum learning, it's very, very widespread, from NLP, reinforcement learning, image classification as well. And so that shows that training times can be significantly reduced. And this makes intuitive sense if you consider how humans learn. Like if you were to learn a new language, you wouldn't just randomly memorize different words. That would take you much, much longer than actually starting from the basic words and then moving on to rarer words that you use in daily life. And it's also considered plug and play because this module, you can consider curriculum learning as like a separate submodule that you could just attach to your original training algorithms. So it's an independent section that you could just implement separately. So you could already use the models that you are currently using. So that's like the basic idea. So let's try to formalize that. The definition of curriculum learning. This is actually the original definition of curriculum learning back when it was first defined in 2009, I believe. So it defines curriculum as a set of training distributions. So Q is a training distribution, and QT would be the distribution at step T. So and P of Z would be the target training distribution. So P of Z is the original data set. That's the original training distribution. And we find that distribution at step T, aka QT, is proportional to the original training set multiplied by some weights. So if you were to, and these weights are from 0 to 1. So from the original training set, let's say this example right here, we can see that these 4 images could have like weight of 1, while the rest of the images would have weight of 0. And that's how you arrive at your training distribution at step T, which is step 1 here. And in order to maintain a meaningful order for the curriculum, there are 3 conditions here that the original definition requires. Number 1 is that entropy gradually increases. So H here would be the entropy, and then we can see that, of course, the entropy at step QT plus 1 would be greater than the step previous to that. And this is to say that the diversity and information should always be increasing, because we want to have a bigger likelihood to sample more difficult images as we get further into training. Second, that the weights are non-decreasing. So you can see that these apples remain in the, or these 4 images remain in the further distributions, because their weights do not go down. Yeah, the weights of T plus 1 is greater than or equal to the previous, its weight in the previous distribution. And this is because we want the training set to always be increasing and not contracting in any way, because we don't want to forget the previous tasks. There are actually categories, or there's implementations of curriculum learning which forfeit this specific condition, but it's been found to have poorer performance. We'll get into that as well later on. And the third condition is that all data is eventually used up, so that the distribution at the final step is equal to the original target training distribution. So yeah, that's all to say that you start simple and you gradually introduce complexity. So yeah, broader definitions exist which forfeit these conditions, and we'll go into some of those when we look at the different frameworks. So now let's look at how and why does curriculum learning work. So one way to look at curriculum learning is to look at it as a continuation method. So a continuation method is a sequence of optimization objectives, or you use a sequence of optimization objectives where you start with a heavily smooth objective function for which it is easier to find a global minimum. And you use that to track the local minima as you slowly adjust that objective to match the target objective. So in that way, training is guided towards better regions in parameter space, because the local minima from easier objectives more likely approximate the global minima. So consider if you start with the target objectives, you could get stuck in the model could get stuck in one of these local minima without ever reaching, like going over this value, this peak right here, because the learning rate might be too low. And so the performance of that model would be poorer than if it were to actually find the global minimum. And you could think of this also as a sequence of unsupervised pre-training. So it's very similar to transfer learning. I think it is considered to be a very sort of special case of transfer learning, where you start with an easier domain, and then you go through multiple stages of transferring that knowledge from easier slowly up to harder and harder domains until you reach your target domain. And next, you could think of curriculum learning as a denoising mechanism. So here you start with a cleaner subset to avoid bad local minimum. So you consider noisy data as harder and cleaner data as easy. And the idea is that if you start from cleaner, reliable data and slowly expand to the full set, then you are able to generalize the cleaner information or the target distribution better. So this left plot demonstrates the data distribution shift. So this black line would be the target distribution. You can see that this represents like the confidence or the confidence of each example. So you can see there's lots of high confidence examples in the target distribution. However, our training set may not always accurately represent that distribution, because with noise, we could have less high confidence examples here in the center and more of those noisy examples in the tails. And so we denoise it by starting with that target distribution and slowly adjusting our training set to match our original training set, which is represented by the red line. So this is done by this plot on the right. So you can see at the start, we underrepresent, or the y-axis here is the weight. So we underrepresent the less confidence examples on the tails, and we only fully represent the ones in the center, which are high confidence. And slowly you shift or you adjust the weights so that slowly and steadily the tails, or the noisier data, is gradually introduced in through these different weight functions, until eventually you reach the point where everything is represented equally. You're using the training set to the full extent. And if you do this, you'll match this left plot here, where you start with the black line and slowly match your training set. And what these two contribute to is that here you can see that the global minima would be more likely reached, so that would lead to greater performance, and also faster convergence, because since you're starting with a heavily smooth objective, you arrive to that minima faster. And this will also lead to better performance on noise data, because you are starting from what you expect the target distribution to be, and slowly you introduce your noisier information. So now we can look at the general framework. So since we're training from easier to harder data, there's two main questions that we need to answer here. Number one is what kind of training data is supposed to be easier than other data? This seems like a subjective question. So how can we actually translate that into something that the model can understand? And second, when should we present more harder data for training, and how much more do we add per step? So that first question can be answered with a difficulty measurer, which decides the relative difficulty of each data example. And there's different algorithms for this, which we'll explore. And also, and the information, or the difficulty that the difficulty measure decides on, is passed on to the training scheduler, which would then decide the sequence of data subsets based on that information. So this diagram shows the main frameworks, or the main categories for curriculum learning methods. And we can see here that there's the predefined curriculum learning, and also the automatic curriculum learning. So let's focus on the predefined curriculum learning for now. So predefined CL is when you manually design the difficulty measure and training scheduler based on some prior knowledge that we have on the data characteristics. So we can like attack this from different angles. One angle would be complexity, which is for images. I highlighted here the common types of predefined difficulty measures for images. With reference to complexity, that could be like the number of objects in the image, because it would have more dimensions. Like text would be like the sentence length, etc. Number two would be diversity. So different images could include rarer elements. Like if we consider the shapes for images, certain shapes like non-convex, like polygons, could be rarer in the data set compared to simple shapes like squares. So the squares, the less rare ones, would be considered easier, while the more diverse ones would be considered more difficult. Another way of designing the difficulty measure is through noise. So for example here, the difficulty measure is actually the data source. So this shows that the way of defining difficulty is not limited to just getting the information from the pixels, but also the source of the image itself. Because if you were to compare an image sourced from like scraping the web versus an image from a data set that was carefully curated, obviously we could assume that the curated data set would have cleaner images compared to ones that were scraped on the web. So in that way, you could set the difficulty based on the source. Next, it could be domain specific. So this is a good example of this is in medicine. where, let's say, you were looking at X-ray films, and the doctor could define like some characteristic of each image that would make it more difficult to diagnose, like I guess contrast, or like maybe the number of like lesions in the image, etc. So yeah, for predefined CL, the researcher or the one creating the training the model is the one that decides how do you define the difficulty. And also, you decide how you define the training or the scheduling of the training. And there's two main types of this. There's discrete schedulers and also the continuous schedulers. So discrete schedulers adjust the training data subset after every fixed number of epochs. So based on the difficulty measure, which we define here, we can divide one algorithm, the baby step, will divide the training examples into buckets. So let's say these are the images which are like plain backgrounds, and these ones are like the multiple objects, very busy ones. You divide them into buckets. And at the start of training, you start with the first bucket. And then at some defined point, at some epoch, let's say epoch 50, then you add on the next bucket while also including the previous ones. So here at the center, I guess you could call this like epoch 100. You'd have the first two buckets while excluding the next two buckets. And there's also another algorithm called one pass, which actually switches buckets and doesn't add. So this is one of the definitions that relaxes that second condition that I mentioned a while ago, where the weights need to be non-decreasing. Because here, you actually put the weights back to zero for the early examples when you're switching. So based on the research that has been done on discrete schedulers, it's been found that baby step actually is more prevalent, more used, because one pass has the risk of forgetting the earlier task or earlier problems, and also the generalization ability of baby step is greater because you're always gradually increasing the training data instead of limiting it to like some fixed size per bucket. So yeah, that's discrete because everything is per bucket, right? It's discrete. And the other type of training scheduler is continuous scheduler, which is based on a function lambda t, which you use a function, and the proportion of easiest training examples below that threshold are included at that epoch. So there's actually it includes here baby step, which is a discrete scheduler, but it just adds it here. You can see that at the start, the threshold here is 0.3. And that would be like the first bucket, everything below 0.3 difficulty. And then at some defined point, 200, then it would jump up to 0.6 and jump up to 0.8 at 400, etc., until the whole data set is used. However, continuous schedulers will use a function to define like how gradual the threshold moves, and anything below that threshold will be added into the training at that step. And this threshold is a value from 0 to 1, and at the last step it must always equal to 1, because at that point you are using the you must be using the entire data set. And there's also a special case where you aim to shift the distribution. So you start training on an initial distribution, and you slowly move towards a target distribution. This is like the denoising I mentioned a while ago. But in this case, a paper was about lung nodules, not lung nodule detection. They actually started from images. So they gave the model only images where nodules were present. And then slowly they decreased the proportion of examples where the nodules were present until they reached the training set, which was extremely imbalanced. And in this way, they were able to see better performance on lung nodule detection, because they were able to train the model on the target proportion first. So now there's a few limitations to predefined CL. First is that it's difficult to find the optimal combination of difficulty measure and training scheduler because there is no existing methodology um, like of deciding which one. You just kind of have to experiment and exhaust your options if you really want to, and then at that point you'd compare. Unless you, of course, you have like some domain expertise, which is also one of the limitations as well, where expert knowledge may be necessary. And even then, if the dimension of like the example features is very large, it could be still difficult even though you have an expert to design the difficulty measure. Next, curriculum remains fixed during training. So since you're predefining the curriculum, it's not flexible to any feedback that the model could be providing during training. Of course, you could like change some parameters and then retrain it, but then during training itself, it's fixed and not flexible. And fourth, we have that what's easy for humans is not always easy for models because the way we make decisions or like the decision boundary for human decisions is different from that of machines. So one way to help solve the limitation of flexibility and difficulty in selecting the specific difficulty measure is to use automatic curriculum learning, which is the rest of the methods shown in this framework. So we'll take a look at self-paced learning first, and then transfer teacher, and then RL teacher. So self-paced learning, what it does is you let the student act as the teacher. So since it's self-paced, it automates the difficulty measure by using training loss of the current model as criteria. So this is analogous to a student who is learning a new topic, and then since they have no teacher, they kind of just like look through the examples, and then if it performs poorly on like a task, then it will consider that as harder. So it'll go through the easier examples first, and then before moving on to the harder ones. And how it's done is that with an example with loss L, you include it if it is below the threshold that is set by the self-paced regularizer. So yeah, if it is below the threshold, then you include it. If it is above, then you exclude it. This is similar to the continuous scheduler that we had earlier in predefined CL. The difference is actually they're pretty much the same. The difference is that here in predefined CL, we are deciding how this difficulty is defined. However, in self-paced learning, the difficulty is decided based on how poor or how well the model performs on that specific example. And so when the model matures enough, we increase that threshold by some value, and we repeat until all images are included. And so we can have multiple regularizers to decide which how do we weight each example at each step. We have hard regularizers, which are binary. You can see here that if lambda, or if the threshold is set to 0.8, anything below 0.8 would have weight of 1. And anything above 0.8 would have weight of 0. That's why it's called a hard regularizer, and it's binary. The issue with this is that it's unlikely that two examples that are considered easy are actually equally important or equally learnable. So in order to add some differences between each example, we can use soft regularizers, which is a function, like it could be like a linear function. So this red line right here, or the blue one now that I'm drawing, this is a linear regularizer. And so from all the way from 0 to 0.8, the examples which are easier, which have lower loss, are considered at weight 1. And then with a straight line, it draws the weights to be at 0.8, it would be weight 0. And there's different functions as well, like logarithmic functions, And it's been found that the soft regularizers, which are these ones, do perform better than hard regularizers because, as I mentioned, it's unlikely that two easy examples are equally important, and this introduces more complexity. The advantages of self-paced learning is number one, it's more flexible and adaptive. Since now we're taking the feedback of the model, and that's how we decide the difficulty, instead of us just predefining it from the start. And another advantage is that it embeds the curriculum design into existing learning objectives. So it's easier to apply. We don't have to think of a difficulty measure because we're just using the current objective as learning objective as the difficulty measure. However, there are disadvantages. Number one, it has the risk of uncertainty at the beginning of training because at the beginning of training, you can't really consider the model to be good at deciding what's difficult or not because the losses are kind of or the weights are all initialized and randomized. So the loss at that stage could not really be very valuable. So there is some uncertainty at the beginning. Another disadvantage is that only the difficulty measure is automated. We're not automating the training scheduler. That's still defined by the researcher. Next, we have transfer teacher, which would now replace the student as the difficulty measure, and we introduce another model to be the teacher. So the difficulty is now determined according to the loss of a teacher model. So originally, this was the student that was deciding what the loss is, but now we have a pre-trained teacher model that we use to determine the difficulty through its loss. And some examples of transfer teacher being used. One is we train the teacher model on a different data set, ImageNet. So it's also like transfer learning because we're using the learned features from a different data set to decide what would be more difficult right now for the current training set, which is different from ImageNet. Another example is training a teacher model on the same data set. So this does look similar to self-paced learning. However, the difference is that right from the start, the teacher model has already matured. It has already gone through the training cycle on the entirety of the training of the data set. While self-paced learning, the student is randomly initialized, right? So and the model evolves. The teacher in self-paced learning evolves through training because the student is the teacher. While in transfer teacher, the teacher model remains fixed, and it decides very similarly to the previous one where its loss is used as a difficulty measure. And another interesting example also is where they used a committee of teacher models on different portions of the data set. So what they did here is they split the data set, and per section of the data set, they trained the model on that. And they used the average loss of the entire of all teacher models to decide the difficulty of the examples. And once again, the disadvantage here is that only the difficulty measure is automated. We're still having to manually define how the training scheduler should be. And that's where we introduced reinforcement learning teachers. And this is very similar to what Rafael mentioned a while ago, where they had reinforcement learning pruning. But instead of pruning, now we're focused on the training aspect. So we would have an RL agent, which would observe the student's learning progress, and based on the feedback of the student, it would choose which examples should be included next, and it would receive a reward based on student improvement. This could be a decrease in loss, or actually even an increase in loss could be used as a criteria for reward, because whether or not the loss went up or down, that's still valuable information to the RL teacher, and it would signify that the examples at that point are significant and learnable. And yeah, so over time, it learns the policy that maximizes student performance. So in this case, both the teacher and student are involved in curriculum selection, because the previous ones don't really take into account the overall performance of the model. Yes, you could have yes, in self-paced learning, the student does decide the difficulty measure. However, the difference is in reinforcement learning, you have like an independent teacher that can decide both the difficulty measure and training scheduler. So in this case, the agent would be the RL teacher. The action is selecting new data for the training, and then the state and reward is the student feedback. So there's many different applications of curriculum learning, and it's actually not just limited to image classification. I decided to just include all here. So for reinforcement learning, let's say you have a very difficult task, and training directly on that target task would lead to poor performance because of its difficulty. So you could implement a curriculum that would slowly guide the model towards solving that problem. So that's reinforcement learning, helping solve a difficult learning task. Next is task interference. So in multitask learning, the model could the task order could not be optimal if it's randomly selected, because previous tasks could like interfere with the future ones if it's not correctly ordered. But with curriculum learning, you set a specific curriculum either with a reinforcement learning agent or predefined, then you could benefit from the information gained on previous tasks. Domain adaptation as well. This is similar to the denoising distribution shift that I showed earlier, where you have different train and target distributions. And also, interestingly, for image classification, the data imbalance could be solved by curriculum learning. This is the example for this is the one I showed earlier with lung nodules, where they started with an easier version of the data set, which is more balanced, and then slowly shifted towards that harder, imbalanced training set. And finally, for noisy and heterogeneous data, this is not just for NLP, but this is just an example where every sentence could be like different lengths. There's different vocabulary that could be used to convey the same meaning, so it's inherently noisy. And by using curriculum learning to focus on the cleaner examples first, you could improve generalization. So how do we choose the best CL method? Well, the first question we need to ask is why we want to use curriculum learning. Well, and there's two main motivations. One is to guide, push the training towards better regions in parameter space. And second is to denoise. So this is to minimize interference of noisy data. And if we want to use predefined curriculum learning, it's best for smaller models and training sets. And if we have prior knowledge about the data, or we have domain expertise. And for automatic curriculum learning, on the other hand, this reduces the need for human teachers. So the researchers has less input on the difficulty measure and the training scheduler. And that makes it more flexible because it can adapt throughout training. And this summarizes the main strengths and weaknesses of each automatic curriculum. So self-paced learning is more efficient and robust, but its weakness is that it's just a fixed strategy. So it's not like our reinforcement learning that can adjust slowly throughout the duration. Then we also have transfer teacher, which now the difficulty is reliable because the teacher has been pre-trained from right from the start. However, the weakness is that you do need that extra pre-training, and that could add some training time to your overall process. And finally, we have the RL teacher, which is the most flexible. However, it is very costly both in terms of time and resources, because especially if you're doing deep reinforcement learning. So yeah, that's a consideration that you need to have. And I'd also like to discuss like a challenge in this field, which is like easiest first versus hardest first. So there is like conflicting research on like which would be best for the curriculum. So easiest first would be like, as I discussed, You start with the noisy, or sorry, easiest first would be like starting with the cleaner and then moving on to noisier data. And it's been actually found that this is best for noisy or heterogeneous data sets, because you could do that distribution shift. And this is best for when tasks are hard to optimize directly, like the RL task a while ago, here where the target task is very difficult. And it's also good for when there are prevalent outliers, because those outliers could be considered like hard, and if you start with them, then you can it could lead to poorer performance. So the other camp is hard dispersed or hard example mining, and there's also been research that this is best for when the data set is clean and balanced, because you are less susceptible to the noise and the outliers at the start of training. And if the data set is clean and balanced, then this would lead to faster and more stable gradient descent compared to easiest first. So yeah, to summarize, we have predefined CL, where here this is manually selected, this is manually selected. Self-paced learning, now this is automatic, but this is still manual. Transfer teacher, the difficulty measure is also automatic, but it comes from a pre-trained model from an external data set, or it could be the same data set as well. But the training scheduler still remains manual. And finally, we have the RL teacher, where both the difficulty measure and training scheduler are automatic. So yeah, that concludes my presentation. Thank you for listening. And if you're interested to learn more about this, I'd recommend this study right here, a survey on curriculum learning, which I based my presentation like a lot of. So yeah, thank you.
Thank you, Christian, for the presentation. So the floor is now open for questions for this last lecture. We have received one question here. This is from Matthew. Since curriculum learning promotes learning features from data ranging from easy to difficult, is there a chance that the features learned from the data considered as easy will be forgotten the moment the model started learning features from the data considered difficult?
Yeah, so that's a good question. And so if I go to, I think this is a good example, because we have here two different algorithms. One is baby step, which always makes sure to include the examples from previous distributions, while we have one pass here which actually switches the buckets. And it's been found that the generalization ability of the one pass, which switches buckets instead of just adding them, is poorer than baby step. So yeah, that's actually correct. If you just simply switch the distribution, switch the data set, then you can forget the previous tasks. That's why more research is leaning towards baby step, which constantly add data and not remove. And if you look at the diagram here, this is sort of like baby step, where you're adding instead of switching.
Thank you. That's actually a very interesting question. No? We call it catastrophic forgetting. The problem being described here, and there's a tendency for that to happen using curriculum learning. If you're doing it, maybe let's call it the wrong way, okay, or yeah, the wrong way. But to mitigate that, as explained by Christian, you do not simply change the distribution of the data, but maybe you continually add and add, using the same small, easy subset of the data set, and you continuously add, so that by the end, you'll have the full training data set. Okay?
Yeah, I believe that's why this condition was added in the original definition. The weights are non-decreasing, so that you don't forget the previous examples.
Okay. Any more questions from our listeners? We've received a lot of interesting questions today across all of the lectures. Since we're actually out of time for today, I actually have a very short question before we end. Maybe I can ask the question. Christian, can you tell us, and this is more of a personal research question, could you tell us how this um, curriculum learning relates to what you're trying to do for your thesis?
Right. So I think my thesis is very similar to since it is medical imaging as well. It's similar to this task right here where they had a very imbalanced data set. So they had like lots of images. Let's say this is like with the with lung nodules and like very few ones with a limited number of nodules in the image. So what I'm interested in is using this distribution shift um, to start off with a data set that is more balanced because in diabetic retinopathy there is a scale from 1 to 5, and my data set, the data sets for diabetic retinopathy typically look like this, where there's a lot of examples with no diabetic retinopathy and very limited ones with severe diabetic retinopathy. So the idea is to start with the distribution where it's more balanced, like so, and then eventually add on that, build upon that, and add the more overrepresented classes, um, so that the distribution is more balanced in the end, or balance to start with, so that the model can generalize on that first.
Okay, thank you. I think those are all of the questions that I have received for this lecture. Um, Thank you for the presentation, Christian. This is a very interesting overview of curriculum learning. We've learned a lot about the different types and different ways on how to view curriculum learning. And hopefully, we can apply this. Actually, this can be applied to any research that you're doing, even if this is not a computer vision project. I would think curriculum learning has um, a way for us to apply it to other domains as well.